Now we look at an example 8.2. Example 8.2 show pumping power requirement for oil flow in a pipe. So in this example, we want to find how much power a pump need to push oil through a pipe. So we look at the data given. So the oil flow in a small circular pipe with a diameter 28 cm. So we need to convert cm to meters. So will be 0.28 meter and a length of 330 meters. And the average velocity of the oil is 0.5 meter per second, and the oil density is 894 kilogram per cubic meters, and its viscosity is 2.33 kilogram per second. So first, we calculate the volume flow rate, which means how much oil flow per second. So the equation will be volume flow rate equal velocity multiplied by pipe cross-sectional area, and using the given value, the volume flow rate is 0.03079 cubic meters per second. And next, we need to calculate the Reynolds number to identify the flow type. So Reynolds number equal density time velocity time diameter divided by viscosity, and after substitution, the Reynolds number is 53.72, and since this value is less than 2300, so the flow will be laminar. So for laminar flow, the friction factor is simple. So friction factor equals 64 divided by Reynolds number. So they give a friction factor of the 1.191. And then we need to calculate the pressure drop caused by friction along the pipe. So pressure drop equal friction factor multiplied by the pipe length over diameter multiplied by density time velocity square divided by 2, and the pressure drop is 156.9 kilopascal. And finally, we need to calculate the pumping power. So the pumping power will be pumping power equal volume flow rate multiplied by pressure drop, and this give a pumping power of 4.83 kilowatt. So the pumping power required to maintain the oil flow in the pipe is 4.83 kilowatt, and is the mechanical power delivered to the fluid, and actual electrical power will be highest due to inefficiencies. And now we move to example 8.7. Heat loss and pressure rise during gradual expansion. So in this example, water flows through a horizontal pipe that gradually expands from a 6 cm diameter pipe to a 9 cm diameter pipe. So before the expansion, the water velocity is 7 meter per second, and the pressure is 150 kilopascal. And since the pipe is horizontal, the head does not change. So the objective are to determine the heat loss in the expansion and to find the pressure after the expansion. So when the pipe expands, the flow area increase, so the velocity decrease. So will be the velocity after expansion equal the area before expansion divided by the area after expansion multiplied by the initial velocity. So using the diameter values of 6 cm and 9 cm, the velocity after expansion become 3.11 meter per second, and a gradual expansion cause energy loss due to flow separation and mixing. So will be heat loss equal the loss convection multiplied by velocity square divided by 2 times gravitational acceleration. So using loss conversion of 0.133 and initial velocity of 7 meter per second, so the heat loss is 0.33 meters. And now we apply the energy equation. Because the pipe is horizontal and there are no pump and turbine, so the equation will be pressure energy plus velocity energy before expansion equal pressure energy plus velocity energy after expansion plus heat loss. So solving the energy equation will be pressure before expansion is 150 kilopascal and pressure after expansion 168 kilopascal. And even though there is a heat loss, the pressure increased from 150 kilopascal to 168 kilopascal. This happened because the flow velocity decreased and part of the kinetic energy is converted into pressure energy in the largest pipe. That's all.